Ross Barron is the state bridge engineer for Nebraska DOT, and he'll be talking to us today about from the lab to I-80, deploying simple for dead load, continuous for live load steel girders in Nebraska.
Well, as Kathy mentioned, I'm Ross Barron. I'm the state bridge engineer for the Nebraska Department of Transportation. I've been in this role for about 4 years now. Before that, I was a design consultant here in the region. So I just want to say thank you to FIU, IBT, ABC-UTC. A special thanks to Dr. Zizi Namini for inviting me to share here today Nebraska's experience with the SDCL system, and just really excited to talk about this and bring light a little bit to the story that Nebraska has and that I personally even have with this system. So I'm going to jump right in. Sounds like there's people who may not know, just like Missouri, Nebraska is right in the middle of the country. So I wanted to share where we're at a little bit. Yes, you may fly over it, but I'm going to do a little pitch for the State of Nebraska Tourism Board. Come check it out. There are quite a few open areas to explore, I guess is the best way of saying it. This is the most recent census data where you can see you've got Lincoln, Nebraska here on the eastern side, and then Omaha is our two major metropolitan areas. But the rest of the state, you can see the western side, it's a whole lot of open area. So Nebraska's got some unique challenges with our state bridges and then certainly with our local bridges. So this is a little bit of what bridges are doing out here in Nebraska. You can see we've got quite a bit of waterways that extend all the way to the Missouri, and this is kind of our main challenge as a bridge engineer. We're not going to have a lot of major interchanges, and our urban areas are going to be mostly in that Lincoln and Omaha area. But you can see we've got quite a bit of major channels that we're crossing throughout the state. And again, pitch for the tourism board. If you want a break, come on out to the Nebraska Sandhills. This is a very real picture of what it looks like. Absolutely beautiful. It's a great way to spend some time away from the city. So please try and come and enjoy it. It's pretty amazing. But you don't need bridges out here, right? But this is what our bridges are going to look like. We have quite a bit of these. We have a lot of braided channels out in this area, right? So wide open, shallow channels. Our highways will extend over them multiple times and a 2-mile period, but you can see this is a pretty conventional bridge for our state highway system. But also we do have these urban bridges, right? So we have the challenges that we would face with any aging urban infrastructure. And you can see this is a steel bridge. I'll tell you, we do a lot of concrete bridges that look a lot more like this. And so this is a great time to have a discussion about, concrete being economical and the go-to choice within the Midwest, but bringing light to this simple for dead, continuous for live system to really evaluate it and see what opportunities are out there for us. So here's a little bit more about the state of Nebraska. We have 15,270 bridges statewide. You can see our state system our performance by deck area there, where we've got about 60% of our bridges in good condition, about 35% in fair condition, and then you can see about 2.4% are in poor condition. So we're well within our goal, our target to have 95% in good or fair condition. So overall, the state of bridges is healthy. We like where we're at, and certainly we still have challenges. We can see a lot of green dots on that map, meaning that our highways are serving the state and our economy very well, especially when it comes to agriculture. So the Nebraska Department of Transportation, we directly own, maintain, program, and deal with about 3,541 state-owned bridges. And then obviously with the local bridges, we have 11,729, and the state oversees the inspection program with those, but they are locally owned. And so the local owners will program that work, maintain them, and quote unquote own them. So I'm going to take you back. Dr. Zizi Namini mentioned the Nebraska Department of Roads at the time, and now it's transportation. We initiated research with the University of Nebraska Lincoln back in, when would this have been, around 2001 timeframe. And really the impetus for this was about 1990, and even before then, the industry was really moving heavily into concrete girders. And so prior to the Simple for Dead Continuous for Live research, NDOT or NDOR at the time and the University of Nebraska did quite a bit of research on the NU Girder series. And so for those of you who haven't heard about the NU Girder, it was a new model following the advent of the AASHTO bulb T girders that produced a wider flange and kind of a more economical shape that allowed us to span differently and just be a little more efficient than those AASHTO type pre-stressed concrete girders. And so we were using these quite frequently. We were still experimenting with post-tensioning. We were evaluating continuity over negative moment regions. And what had become apparent was that the simplicity of the pre-stressed concrete girder was outweighing some of the complications with erection of steel continuous girder systems. And at this time, continuity obviously was very important. It allows you to use a shallower section, and there are big advantages to that. So you can see in the middle there, you've got steel girder erection and you've got false work needed for the splice. Now, not always do you need that, but you can see that's quite an extra step versus just setting a pre-stressed concrete girder from substructure element to substructure element. And therefore, a really an expert in research and bridge engineering at the time, Dr. Azizi Namini, was at the University of Nebraska, Lincoln. And he and his team worked with NDOT to basically evaluate whether we could mimic the pre-stressed concrete girder system with the steel girder. And that's what we're hearing about today. So that's a little bit about the history of how we got here. And so you can see, and we heard it earlier today, that NDOR at the time, we were there for the tests. Funny enough, I was actually an undergrad at the time, and I remember going into the lab at University of Nebraska and seeing this. And so it's kind of a neat opportunity for me today to present about how NDOT is dealing with these bridges 20 plus years later. So this system, this research, you can see the bridge above. This is what it looked like before. We needed replacement. We had a typical 4-span steel girder system, continuous, and what we were accomplishing was to eliminate those 2 exterior piers and go continuous with a section that is about the same structure depth as it was before. And so that's a huge improvement from going back with another 4-slab bridge. And you can notice very slightly, there's a minimal grade raise. That's very important on a bridge like this, that it allowed us to not have to grade out a lot of the area and affect, you can see the apartment complex in the background, affect those area buildings. So NDOT was there at the beginning, and we implemented 3 of these systems. You've heard about them a little bit this morning. I wanted to show you where they're at. So we have, the first was an urban bridge in the Omaha area, and it crosses Interstate 680 in Omaha. It's a north-south route, and we'll talk about that. And then the other 2 were along I-80. So for those who don't know, I-80 is our main interstate in Nebraska. So it stretches all the way from the east side of the state, kind of travels across, follows the Platte River, and it goes all the way across. So that is a key interstate connection for Nebraska Department of Transportation. So you can tell the fact we built 3 of these over an interstate can tell you that really the focus of that research was to not necessarily take the MoDOT approach of using these on smaller spans, but really the intent here was to showcase that this system can be placed over an interstate where disruption to traffic is very impactful. And so we really wanted to provide that proof of concept, and you can see the results. So I want to talk about the bridge over I-680 first. So this is Sprague Street in Omaha, Nebraska. This was built in 2003. So right away you can see this is an 8-lane interstate with sizable shoulders, and we have a 2-span bridge. So you can see we've got an MSE wall or a precast wall system on either side to kind of bring in those abutments. And then sliding to the next page, you'll see the configuration a little bit. So we've fixed the superstructure at the pier, the bearing condition, and then we've leveraged integral abutments and expansion bearings at each end. You can see it's a 2-lane bridge with sidewalks, so it's a pretty typical urban bridge. It's connecting 2 neighborhoods, but again, the key constraint as any state bridge engineer will tell you, is please don't close that interstate. And so when we talk about, you know, if there's a need for splice locations or erection timing, you get one overnight closure. And because of that, a pre-stressed concrete girder or a precast system, it just comes out as having a lot of advantages. So this bridge, like I mentioned, was built back in 2003. So that makes this bridge, I think I put 21, but for those who are better at math than I am, apparently, I put 21 years down. So it's a 2-span. Each span is nearly 100 feet, so 194 foot total. So today I wanted to share just high level the NBI condition ratings, right? So this is how the Fed highway system works, where we will rate our deck, superstructure, and substructure anywhere between 1 to 9, 9 indicating the best condition, and 1 being that bridge is closed and it's about to fall down. So we don't let our bridges ever get to 1. But these are kind of a good quick take at the health of the bridge, that this is what the inspectors have indicated. And so you can see here that the deck is indicated to be in good condition. The superstructure is an 8, which indicates it's in great condition, and the substructure an 8. So overall, you can see just from the data that this bridge is doing very, very well in its condition. So now to the details. We've seen some of them a little bit, and I just wanted to share a little bit of my perspective, that you can see what's happening during construction here, where on the left, we've got a picture of both girder systems are in place. You know, they're setting the formwork. We do use steel stay-in-place forms here, but it's a very, very easy, simple approach with traffic going underneath. So you can see it's minimal disruption. Now at this time, it looks like it's head-to-head traffic and there's nothing going on here. But you can see this really showcases how shallow that system is. And then we've seen this detail before. It's worth noting that, you know, we still have these wires hanging down, that these sensors were invaluable for the research. But it's really cool to see this detail, and just, I appreciate the simplicity of it overall and the ease of construction. I think one thing we heard from this contractor and every other contractor is, oh, we thought this was a research project and it was going to be really challenging, when in reality, this was very, very easy and straightforward, very economical, and really, really simple to fabricate the end of that girder. So the one thing that concerns us in Nebraska, maybe more than anything, is we know our substructure and our superstructure, our girders, are going to be okay for a long haul. But our deck, we are a state that salts our decks, right? We have very, very harsh winters where we have freeze-thaw cycles that happen within the same day, where we'll get a lot of snow and it'll melt the next day. So we have rapid temperature swings. What that means is we'll go out and we will pound this concrete with salt, you know, throughout a 6-month period potentially, to ensure that they're safe to drivers. So the deck condition after 20 plus years, there's no overlay on this bridge. This is the original cast in place concrete deck. We see no signs at the pier of any major cracking. There are narrow random cracking, but we were successfully able to seal those. And so you can see the deck condition, we've got a little bit of rusting, but that's indication of nothing more than the drainage going that way. And it's likely fertilizer more than anything. You can see some white spots, but we think that's paint. So again, the deck condition on this has performed very, very well over this 20 plus year period, and we're very happy with that. That would be one of the concerns, that we would cause adverse cracking to the deck. So the intermediate diaphragms, another area where we were thinking, oh, what's going to happen here? Research showed it would be fine, and sure enough, there are no issues whatsoever with this diaphragm. So you can see there's minimal cross frames near the support. We certainly got, these are our sensors dangling down. I don't think we've gone out and tested them anytime recently. So you can see it's very clean, and it's working very, very, very well. So the one thing we have seen is at the abutments, we've seen some salt collection happening at the ends. You can see, if you look very, very closely, some scaling along the steel at the ends, mainly along the fascia girders. And then you've got some rusting of your stay-in-place form deck pan. Really, all that is indication of is, again, you can see the amount of traffic that can travel down here. So you're going to get a lot of salt spray coming up and hitting these girders, particularly the fascia girders. And so we're just seeing an indication of that. And this is weathering steel, so you are going to get kind of some advanced corrosion from that salt exposure. For those with a keen eye, you can see there's a concrete pad here. Basically, that was just an erection pad to help support the girders during construction, and then to fill in that gap with the MSE face. We think because this is an integral abutment, you're going to certainly get some thermal shifting back and forth. And so we think over time that's just settled down. We've had a watch on that for a while, and there's not really any concerns, but we're keeping an eye on that. So kind of the recommendations coming out of this, a review 20 years later on what do we think about this system. You know, this bridge indicates that there should be no concern with continuing to use this method at this span length with this configuration of the integral abutments. The limits, the structural depth limits were met, that a pre-stressed concrete girder would be about the same height. The erection was very, very simple. Ongoing maintenance recommendations are very, very minimal. We do intend to zone coat those fascia girders at the end to protect from that salt spray. And because this drip bead detail wasn't working perfectly, we think we had water running along that flange. And then, as with any bridge about this age, you want to check for settlement of the approach slabs, the joints. Certainly we need to continue to maintain, but again, these are all things that we would normally be doing. And so it's worth noting, we have no program to work at this time. Typically we'd be looking at a redeck around this time or an overlay, but we haven't programmed anything at this time. So overall, this bridge is not a concern. It's working wonderfully for us. So now I want to move to more towards I-80. So you can see the span length on this bridge. This is out near Grand Island, Nebraska, at an interchange out there. And this is a tub girder that we saw earlier from Dr. Azizi Namini. And real quick, it's worth noting again, this weird stuff, this alien looking thing, that's just sensor wires. So don't be concerned about that. Okay, so this bridge, again, probably bad math, fuzzy math, it's not 21. I think by the time it opened, it's probably about 21 years old. So it's two span, 139 feet, 139 feet balanced. You can see it's a similar configuration where we've fixed the pier support, and then we have expansion and similar integral abutments at each end. So Interstate 80 in this area, it's a 4-lane divided interstate. You can see here there is an on-ramp coming on, so it's got that additional lane. This, instead of using MSE walls on this bridge, we use just typical concrete slope protection. And it's worth noting we do have pipe piling on this one instead of an H-pile with those integral abutments. So you can see it's a fairly shallow structure depth. That's a nice, elegant shape. And I'll tell you, that's something that any bridge engineer is going to want to see, these long, shallow shapes that follow that crest over the interstate. So it's a really elegant looking bridge. So construction in 2003, if you were on earlier, you would have seen some of these pictures. The construction is very, very simple of these. This is like setting any beam, except one thing to note, these are, you know, these tub systems are very, very elegant, meaning you've got cross frames on the interior. They're stable once you place them. You know, you got a 2-crane pick here, but you can see that the truck just drives right down that road. They pick it up, lift it, and put it into place. They've set some down here, and it goes very, very quickly from what I've heard. So again, the contractors really, really like this system. You saw it with Brian's presentation earlier, and you'll see it here where we've used a simple integral detail where you just take the piling up to the bearing seat and you weld a channel across and you just plop those things right down on the abutment. So it couldn't be any easier for a contractor to build. You can see again, what this speaks to is the stability of the system. One thing I'll note a little later, there are no cross frames. There's no external cross frames between these beams. And so when you think of erection time and the time that you're closing to traffic, I bet in this picture, even though we don't see any cars, that this was open to traffic while this picture was taken. Here's an indication, again, no cross frames. This could, in my opinion, not be any more elegant than it is. You can see we use stay in place forms. This is a recent inspection photo, so you can see things that you would normally expect. You've got some rust staining. This is weathering steel. It's actually 100 KSI. Weathering steel that we've used, so certainly you've got the typical rust staining. You've got some areas in here at the intermediate diaphragm that were patched during construction, and we'll talk about that a little bit. But overall, it's looking great. So quick detail towards the end so you can take a look at this. So just like the I-girder, you're going to have this fabricated bar on the compression flange. And then here we had turn down plates at the tension face as well at the pier, just at the pier. And then a really, really nice detail to simplify construction that was easy to install is this bulkhead, so that you can just pour concrete right up to it. Since you're pouring your diaphragm and threading bars through these holes, this bulkhead made it very, very easy. And then if you'll notice, you've got shear studs on the interior here, and that's for that compression flange bracing where we're going to pour some concrete kind of through here to brace that bottom flange. So it forms up pretty easy. I thought a really nice detail here as well, and the turn down was certainly, it looks like a normal turn down. We're threading the bars through, but was these bearing blocks that from a bearing perspective, this is very easy. As I mentioned earlier, this is a fixed pier, so everything gets encased. So really this is just temporary for construction. But again, you can see how easy this is to form up. And how easy it is from a detailing perspective with the reinforcing. It is worth noting we did use 5 KSI concrete in that diaphragm due to some of those additional forces that were in there. So here's a picture from the interior of the tub, and this is showing those studs and showing that compression concrete that we would be placing after this. A really nice detail. It's been performing well. Unfortunately, I don't have pictures of what it looks like today, but inspectors have noted that it's in great condition and they're seeing no distress at all. So this detail has been working very, very well for us. The one thing to note that we did see on this, and this happened during construction actually, you can see the sensor there in place. You can see some of this cracking, right? And so really it's delamination happening. These are the pocket ties, right? They're just the holes that haven't been grouted. But we did see this during construction. There was discussion about how to alleviate that, and it was implemented on other bridges. There wasn't really any concern. It hasn't grown since construction. We did do some epoxy crack injection, and so those have been sealed, and we've seen no further movement of that deterioration that happened at construction. One issue we have been is that the deck is an 8, the super is a 5 in the most recent inspection, and then the sub's doing just fine. So that super rated a 5 means it's in fair condition, that there's some issues with it that we want to keep an eye on. And so if I go back to where I was, you can see we're seeing some scaling issues at the end of this 100 KSI steel tub. And we think it's an indication of the similar salt spray we saw on that I-80 overpass, where salt is gathering around that bottom flange and it's just scaling it. We also think, so this is actually, this is the exterior, but you can see you've got salt spray here. We've done some additional studies. We've climbed up in there and we've been monitoring some deterioration on the inside of the tubs. And we think there might be an airflow issue where some water is getting in through the back wall of this bridge. So we're tracking that, and we think we've got a good fix. And so one of the things we do want to do with this superstructure, and that we would recommend looking at in the future, is improving airflow within those tubs. If the back wall detail we have, if we're using the same dimensions, maybe we'd want to deepen that integral abutment a little bit just to provide a little more concrete protection to it. And then we do want to enhance some of the abutment drainage details to make sure water isn't getting into those back walls. That because we've embedded this steel in the concrete, we want to make sure that water is pushed away from it. And then if we were to build this bridge today, we likely would have end zone coated those steel tubs just to prevent any of that deterioration that you're kind of seeing here. And then it also helps with just the rust staining effect. And so it just helps kind of pull that water and wick it away. So ongoing maintenance on this bridge, it's fairly minimal. We are monitoring some of the issues with the abutment, and we do intend to come in and redo that drainage. We're looking at whether we want to fix any of this concrete by tearing it out or simply just doing some crack injection and continuing to monitor. But we will be replacing the approach slab, and then we will be kind of doing some treatment to that steel at the end. So still overall, the bridge is performing very, very well. The issues with the steel shouldn't detract from the applicability of the system and the elegance of the configuration. Okay, so now to another I-80 bridge. This was an ABC application that we saw earlier. This is between Lincoln and Omaha over I-80. You can see that it's a 6-lane divided interstate today. Similarly, you know, shallow structure depth, very elegant long spans. We still have fixity at the piers and we still have expansion at the abutments. We did on this use an MSE wall to bring in those spans. So they're about 137 feet each to about a 274 foot long total bridge length. And then this is on a skew. So this is a 24-degree left-hand back skew, and you can see it here. Left-hand back, meaning that the left-hand side is skewed backwards. And you can see from the condition ratings taken last year, this bridge is in excellent health for a 21-year-old bridge. So we are very, very happy with what we're seeing out of the inspection reports on this ABC application of this SDCL bridge. This is also a tub girder, and this is the one that had a deck cast prior to placing the girders. So this is the layout of the deck panels. This is the center line of girder, if you can see my mouse here. And this is how all the panels fit up. This isn't an easy thing to do with a skewed bridge, but the intent here is this is I-80 traffic between Lincoln and Omaha, which is a very, very vital connection for the state. And limiting the amount of closure time on I-80 should be desirable for any bridge we construct. So this was a good test case to evaluate how we could accelerate construction even further by pre-placing that deck. What was nice about that is that we saw it earlier with Dr. Azizi Namini's presentation, that they had these girders on site, the tubs, steel tubs on site, and they were casting the concrete right there. And so it was there was plenty of area and it was really easy to do. The contractors had no trouble based on what we heard. Very, very simple, and we got an excellent product out of it. So no issues with placing that concrete there. The lift was a little harder, right? I mean, you've got all that deck concrete on there now. So it was still a 2-crane pick. A little heavier cranes. The contractor didn't have any problems, particularly given that we had plenty of space to work with out there. So this is kind of a pick, the pick lift, the lifting of the girder. You can see the first one's down, the other span's placed. Pretty easy nighttime closure. They've come out and they've just put some dirt out. They marched the crane out there. They've got the girders up on the bank already with the deck on them. And they just swing these things out. You can see this one's just going to extend it out, and this one will swing over and just set them into place. Following that, you've basically just got your closure pores and you're good to go. So one thing to note with this system, again, with the erection being very, very elegant and easy, you can see how clean this is. There's no external cross frames whatsoever. Because we don't have stay in place forms, you can see the bottom of the deck. These 2 lines here indicate the closure pore that they had to do between the pre-placed concrete deck on the tubs. But you can see this is a picture taken last year that the deck condition looks excellent for a bridge this age. And so speaking of cross frames, I mean, this is very minimal cross frames in here as well. And one thing to note, I'll note this too, when I was going back and doing some research on this, the vertical webs of the tub really simplified fabrication. It's something that we're studying a little bit more, that too often you'd kind of see a trapezoidal section where you've got an incline to those web plates. But the fabrication process with the vertical plates went very, very well. It was very easy. There was good comments and good feedback back from the fabricator that we saved a lot of money by having these be square tubs. And you can see here the intermediate diaphragm. Unlike the other one, there are 0 issues with this concrete. Similarly at the abutments, even with the skew, you might expect to see some cracking maybe out here or maybe in here, but this is actually a semi-integral system now that I see it. It's performing very, very well with no cracking or anything like that. You can see these are the access holes we use to get into the tubs. It's very important when you have tubs that you still have inspection access to get inside and evaluate the interior. You'll notice the ends of these tubs don't have the scaling we saw on the other one. You can see on these fascia girders a little bit of a profile of salt spray coming up, and you can see some discoloration throughout as you look longitudinally. If you look hard at your screen, you can see a slightly different orange And so we do expect that scaling will occur at some point along these girders, that we'll need to do some end zone coat painting, but overall no concerns at this time. So some recommendations coming out of this. The biggest one here is if you can eliminate lateral bracing on a steel girder bridge, try and do that, because from a rapid erection perspective, it provides a great product that allows you to really open that to traffic quickly, so not really interfere with traffic operations. The skewed configuration showed no signs of distress. We would have no concern with going with this same system with a skewed configuration. And then pre-placing the deck, this deck does have an overlay on it. As we saw earlier, it's a 2-inch silica fume overlay, but it's performing very well. This has provided a very durable deck for a low ADT road. Now this sees a little less salt than you might see on the interstate, but it's a great application, and you can see that from this picture that we have limited water leaking through that deck. And then the limited internal cross-frame bracing is very effective. It allows us to climb in there and inspect, which is very important, and it keeps the weight down. Maintaining the vertical webs I mentioned was a good design decision, and then that 2-inch concrete overlay is doing very well. So for this bridge, we have minimal upcoming work. We got minimal maintenance, you know, the typical stuff you might see on a bridge, like cleaning and replacing joints and washing decks and clearing out drains. And then we're just going to continue to monitor those fascia girders, and eventually we'll probably need to end zone coat those. Okay, so NDOT perspective 20+ years later, this SDCL system, it's such a simple design. I've spent a lot of time as a design engineer, and I think there's a lot of applications for this that make it just as simple as a pre-stressed concrete girder would be. I think it's clear from the contractor's perspective, the construction is very simple. It's, again, you're just putting the beam down and you're pouring some concrete around it. What we've been seeing from these bridges is that we have a durable design, that we don't need to worry about the details work. They're straightforward, and further, it offers the opportunity for accelerated construction. There will be times where a steel profile is needed just from a structure depth perspective, and being able to place these girders without splice locations will help us out quite a bit. I think one thing I did want to share though is what's interesting about this is, why does NDOT not have more examples? And this was a question I asked myself while preparing for this presentation, and I don't have a good answer. I think for all of you listening today, whether you're working for a public agency, a DOT, or whether you're a consultant, I want to bring awareness to the fact that this system was researched, 20+ years ago, and yet we're not seeing wide adoption of it. That I think bringing attention to this will hopefully make us aware that this system is a very viable alternative to a pre-stressed concrete girder, particularly when constrained by things like vertical profile. So I wish I had more examples, but I think the key lesson here for us is, let's make sure we continue to explore these innovations, that we continue to build, that we leverage the good research that's been done, and that's NDOT's intent following this, and what we're seeing, that you will see us doing more alternatives that include this SDCL design. So with that, I just say, if you see orange cones and slow signs, please slow down. There are workers working. And also, just a reminder for everyone, buckle your seatbelts, please, and put your darn phone down when driving. My contact info is there if anyone wants to reach out, has any questions, or wants more information.
Thank you very much, Ross. That was a fantastic presentation.